Okay. Okay, so hi everyone, and today's talk is called Towards a Theory of Metacognitive Agents. So what are we going to talk about in this talk? We'll briefly talk about what do I even mean by metacognition for the purpose of this talk. Then I will explain the basics of the formalism that I started to create in order to describe metacognition. Then we'll talk about a particular sort of interesting case study called meta-reinforcement learning. And in the end, if we have enough time, we'll also talk about recursive meta-learning, which is a form of recursive self-improvement. So first of all, okay, so what is even metacognition? What are we talking about here? So roughly speaking, by metacognition, I mean using cognition to improve cognition. So example of this would be cognitive load balancing. So what does it mean, load balancing? It means, for example, I'm deciding, which problem I should spend more time thinking on based on my experience and things I learned before. So here I'm using something that I learned in order to make my cognition more efficient, in order to do better load balancing for the cognitive resources or computational resources I have in my disposal. Another example is things like rationality techniques. So for example, I mean, it could be like simple things like doing lists of pro and con when making a decision, right? That's a technique that you learn, right? Or more sophisticated things like using probability theory calculations to make decisions. So that's all of the things are things that are learned, and they improve our process of reasoning about things. So, and all of mathematics can also be thought like, I mean, it's kind of stretching the traditional definition of modest metacognition, but from my perspective, all of mathematics can also be regarded as a form of metacognition, because like when you're researching mathematics, you're learning things about some abstract things, not directly about the world. And then you use those abstract things that you learn to come up with better algorithms of learning things about the world or doing something in the world. So what is interesting, I mean, one of the things interesting about this is that existing theory of agency, so existing mathematical models like AIXI or the theory of reinforcement learning, don't have much to say about metacognition. For example, in reinforcement learning, we're talking about learning a hypothesis out of some class of hypotheses, but there is no feedback. So the hypothesis we learned does not influence the algorithm that we use to learn other things. So here I set out to create a new formalism that would capture those aspects of reasoning and more specifically aspects of intelligent agency. So we'll start with talking about the actual formalism.
I have a question.
Yeah.
Should we wait with questions or can we ask them at any point?
I think you can ask them at any, I mean, I'm sure you can ask them at any point, and worst case scenario is that I'll say something like, we'll go back to that later. And then maybe I'll forget about it and you'll remind me at the end of the talk of something.
Okay, then I have a second question, which is, could you give an example of things that lay at the boundary of what is still considered metacognition, such that I can bound the concept?
that lay at the boundary. I mean,
or things that are closely not metacognition and things that are close to metacognition.
I mean, for me, like things that you have in traditional reinforcement learning theory are not metacognition in the sense that we're talking about algorithms, how to learn properties of the world, but the algorithm is kind of static. Like we're not, like there's, the process of learning doesn't influence the algorithm we use in any way. So like for me, an example of not metacognition would be basically all of classical reinforcement learning theory. And
so for example, if we learn something new about the world, then that wouldn't count as metacognition, because the algorithm that we use to, like, let's say, make a prediction of what happens next is not changed.
yeah, I mean, like we have new, like we have updated our world model, but the process of updating our world model is not in itself affected by this update. It's like very like one directional kind of downstream thing and not a closed loop thing.
What if we learn a new algorithm that allows us to manipulate the world in a particular way, but not our own, but not our cognitive processes? Like that's like I learned to fly a helicopter or something.
And if you learn to fly helicopters, then that's not metacognition. If you learn something, some abstract thing that can then be used to in multiple different problems, you know, like, so then maybe it is kind of enters into the domain of what I call metacognition, right? Like if you learn some abstract techniques that you will then can turn out to be useful both for flying helicopters and for, I don't know, training orangutans, then it will, yeah. So I guess we can discuss it more when we have like a more concrete like formalization.
All right.
Yeah, so kind of standard theories of agency, they use what I call the standard cybernetic framework. So the standard cybernetic framework says that there is an agent, and this agent interacts with an environment. So it has some action, some set of actions it can take. For example, maybe it's a computer connected to a robotic arm, and the actions correspond to like different commands that the servos of the arm can receive. And like it also has a camera, which is, you know, recording, which is like looking at the world. So this set of observations corresponds to like all the possible images this camera can transmit at any given like frame. And then we talk about like policies that the agent can execute, which are like mappings from the histories it's seen so far to the next action. In environments, which are mappings from the history so far to probability distribution over observations. And typically we're maximizing, like the agent is trying to maximize the expectation of some utility function, which a lot of the time is going to be like a time discounted sum of something which depends on the history so far, and called the report. That's like standard stuff. So my proposal is to modify this framework into something that I call here the bipartite cybernetic framework. So now the agent is made of two parts. There's what we call the core and the envelope. The core okay, so we're commented that PEAS is sometimes used for the cybernetic framework, but okay. So the core is like still connected, it has some actions and some observations connected to it. And the envelope is just a computational device. Like it's something that can run programs and produce like, you know, whatever the output the program produced. So now the action set of our agent is kind of consists of comments to the server and comments to this computational device. And the observation set consists of inputs from the outside and inputs from the computational device. For example, maybe it can send a command to run a particular program, and then it gets like an answer that the answer is 7, or probably a better formalism would be to think of like starting and stopping some computational processes that run continuously and have input streams and output streams. So this whole system can be regarded as the agent which interacts with an environment. But on the other hand, this entire system, like the environment together with the envelope, can be regarded as the domain of the machine learning. So the machine learning algorithm that's running inside its core is not just building a model of the world, but it's also building a model of this envelope. And what this envelope is actually just the stand-in for kind of abstract computational facts like 2 + 2 = 4, which we can also learn using this learning algorithm. And notably, those two things, they overlap. So the fact they overlap means that in some sense, our agent is capable of doing introspection. It's kind of capable of looking into some part of itself. Okay, so in order to, so one thing notable about this is that this framework is inherently non-realizable. So, in learning theory, we talk about situations that are realizable when I have a hypothesis that explains the data exactly or like stochastically, whereas the situations which are non-realizable, in which I don't have such a hypothesis, and I should do approximations and something else. So here we're inherently the non-realizable regime because, well, first of all, of course, just the environment is very computationally complex, so we're not going to be able to describe it exactly. But even if we're just, were to ignore that, just this part is already non-realizable in itself, because this envelope can run some complicated computations, and like the agent cannot, cannot have a hypothesis that predicts exactly what the output of every possible computation would be. It doesn't have enough resources to do that. So we need to use some framework that accounts for non-realizability. For example, infrabayesianism. So infrabayesianism, I'm going to kind of do a super quick recap of what is infrabayesianism. So in ordinary Bayesianism, we describe our beliefs by probability distributions. So probability distribution, so delta X is like the space of probability distributions over some space X. Infrabayesianism, we describe our beliefs by infradistributions, or in the simplest case, Creedal sets. So Creedal set is a closed convex set of probability distributions. So box X will stand for the set of closed convex sets of probability distributions over the space X. Ordinary Bayesianism, the thing we want to maximize is, like, we have some function U on our space, whatever the domain is, which is the utility function, and kind of the metric we're maximizing is the expectation of this utility function with respect to, our belief zeta. So in infrabayesianism, the analogous thing is doing the minimum over all zeta inside this Creedal set theta capital of the expectation of U with respect to zeta. Now, when we're going into the cybernetic framework, we also talk about environments, right? So environment can be used to describe a hypothesis about the world, or a prior about the world, or even a ground truth about the world. Yeah, and to every such environment, we can also give it a different mathematical description, an equivalent description, as a mapping, or more precisely, a Markov kernel from pi capital, which will stand for the space of all possible policies, to probability distributions over infinite sequences of actions observations, which I call destinies. Yeah, Jobs?
Yeah, just a short question. I'm puzzled by the environment apparently not having any hidden variables. Is that general enough here, or do we need any hidden variables that cannot be observed and like a hidden state?
So you can always fold the hidden state into the definition of the environment, as long as you're like Bayesian, because you can say, okay, conditional on, like there's some hidden state. I don't know what the hidden state is, but I know like what is, initial probability distribution and what's the law that according to which it evolves. So then I can say conditional on this being the history so far, what is the probability distribution over the next observation we're going to see? So effectively, we're just marginalizing over any hidden state.
So basically what you call environment is actually a model of everything that we could possibly know about the environment.
Yeah, it's kind of the projection of the environment on the observable thing.
Okay, thanks.
Yeah, exactly. So yeah. So now in infra-Bayesianism, the analogous thing is what's called a law. So a law, lambda capital, is a mapping against from the space of policies, but this time to creedal sets over destinies, such that there exists some set of environments E for which, for every policy pi, lambda of pi is equal to the set of all mu hat pi for all mu in epsilon. So there's some set of environments that kind of generates kernels. So this is what we call a law. Those laws in infra-Bayesianism, they serve the role of hypotheses and also priors, but not ground truths, because this is kind of inherently subjective in some sense. Like you cannot, like the ground truth, something happens, but here you allow for this Knightian uncertainty. Okay, so that's a super brief recap of infra-Bayesianism. Like, okay, how does our new framework modify this? So in our new framework, I introduced the notion of a metacognitive law. So how does the metacognitive law works? So let P stand for the set of all programs that have no input and that produce 1 bit of output. And gamma stand for mappings from P to 0, 1. So in other words, gamma is like assigning to every program an output that this program could output. It's like some counterfactual way in which computations could behave. Like maybe 2 + 2 = 5, and the sign of 1 equals 3.7. I don't know. And now we're also going to have some C, which is a subset of gamma times the space of destinies, which I call consistent meta-destinies. So what is the C? So remember that those actions and observations, they include both interaction with the environment and interaction with the computational envelope. This means that if I'm looking at a particular destiny, this destiny might be saying, I ran a particular program on my envelope and the answer was 7, according to the observations. So this means that there is some constraint that relates what the computational universe and the destiny that I actually observe. Like if the computational universe says that some program returns 7, and this destiny says that this program actually returned 5, that they're not consistent. So the set of consistent things is called C. Now we have this meta environment. So what's a meta environment? So meta environment is a pair of mu0, which is a distribution over gamma. So this could be like a Bayesian belief over like a Bayesian uncertainty about computations. And mu1 is a mapping from gamma times histories to probabilities distributions over observations. So in other words, mu1 is sort of an environment parameterized by gamma. And those two things, we can combine them and build mu hat, which is a mapping from policies to distributions over C. in kind of the obvious way. So we just like, given any policy, first of all, we just sample mu0, doesn't matter what the policy is. And then we kind of unroll the interaction of this policy with this mu1, where we plug in the thing we sampled in the first stage as the first argument. So that gives us like this kernel mu hat. And now we can define what a meta law is. So meta law is now just a mapping, like continuous mapping, like all this from pi capital to box C, such that exactly like before, there exists some set of environment E, such that for every policy pi, lambda of pi is exactly the set of mu hat pi for all mu in E. So now we have notions of hypothesis for a metacognitive framework, in which a hypothesis, it kind of says things both about abstract kind of Platonic things like computations, and both about the actual external world, and potentially about the relationship between those two. So one way to think about this kind of epistemology, this metacognitive epistemology that comes out of this formalism, is that the kind of first part that corresponds to mu0 is like quote unquote mathematics. It's like facts about computations. Oh, sorry. Like fact, or at least computable mathematics, you know, like some facts that could be true about computations, or like my beliefs about computations. Whereas the second part corresponds to my beliefs about physics, you know, about how the external world behaves, modular computations. So why is it modular computations? Because imagine, for example, that I've discovered some theory of physics, which is described as some mathematical equation. And usually it is not feasible to actually simulate this equation and see what comes out. So saying that I have learned that this equation describes physics is a sort of implicit description of the world. It's implicit because I cannot directly, I don't make predictions based on this equation directly, like, but if I combine this knowledge with my knowledge of mathematics, then I might be able to use this equation to make some inferences that will actually tell me things about the actual world. So this, you know, it doesn't have to be literal physics. It can be all sorts of things that I know about the world, but this is sort of a way of thinking about it. Okay, so now we make the analogy to humans, then arguably humans also work in a sort of analogous way, right? Because humans also have outputs like to the external world. So if this is a human, so I can move my hand so that I can affect my environment, right? And I can look at things with my eyes, so I get some observations, but I also can think thoughts inside of my head, right? Like when I think thoughts inside of my head, I can run computations, like I can literally calculate something, like what's the sum of those two numbers? I can calculate it in my head. Or I can think about other things, but for example, maybe I'm thinking whether to live in a village or live in the big city, you know, but I'm kind of having a conscious, explicit process of like weighing up the pros and cons and deciding. And you can argue this is also some sort of calculation, some sort of algorithm that I'm running. So you can say that for humans, kind of, maybe it's kind of speculative, but maybe all of like conscious thinking or system 2 thinking is sort of analogous to running programs on the envelope in this picture. Because like this is also something that's probably learned, right? Like we learn how to think more useful thoughts, or like what kind of cognitive algorithms to use to solve our problems. Okay. So far we kind of described the formalism in a very kind of abstract, high-level way. But now I want to start to add a little bit kind of more detail to it, kind of flesh it out a little bit, not a lot, but just a little bit. But for example, we're talking about like hypothesis about gamma. So like beliefs I have about progress, but that sounds like something very complicated. How would you even go about, like, suppose I actually want to design an algorithm for a metacognitive agent. What kind of hypothesis space would I employ for reasoning about programs? So here, for example, one natural thing to do is use tree automata, right? So like, for example, often we use, like in theory of machine learning, we often have hypothesis spaces made of some kind of state machines like Markov decision processes or hidden Markov models or whatever. So here we can also use a type of state machine, which is a tree automaton. So a tree automaton is, so I'm guessing that most people here know what a word automaton is, right? So this is just your usual deterministic finite automaton. So there's this set of states, Q capital, there's an initial state, Q0, there's the transition function given a state, and there's an alphabet sigma, and there's a transition function, given a state in an element of the alphabet, what the next state is, and there's some set of accepting states, which I have left out here. A tree automata, so specifically a bottom-up tree automata, is also has a set of states Q. But now instead of single alphabet, it has a graded alphabet. So for every arity, which is like some number from 0 to some finite amount, it has some alphabet sigma r. And we have a transition function delta r, which takes r states in an element of the alphabet and produce an element of Q. And this way you can process, instead of processing a string of symbols in the alphabet, you process trees. So if I have a tree where every vertex in the tree is labeled by something from the alphabet with the arity corresponding to the number of children in this vertex, then I can apply my automaton to this tree. So to every leaf, I just apply the delta 0. Right? Like if this is C, this leaf gets the state Q0 equal delta 0 C. This leaf will get the state Q1 equal delta 0 D, so on. When I go here, I look at the free states I have here, Q0, Q1, Q0, and apply delta free, because I have an arity of free here, just those states and 8, and I gave the state a did vertex, which is Q2. And this way, every state we're propagating bottom up, every state gets labeled by, every vertex gets labeled by a state, and then we get some state in the root, and we look where it's accepting, and this determines where we accept the tree, for example. So why is this kind of an appealing formalism? For this purpose, because programs are also trees, right? We can describe programs by syntax trees. For example, if we're using lambda calculus, and every expression has some tree where the leaves are kind of the atomic terms, and every vertex, which is not a leaf, is labeled by some way of constructing a new term from the atomic terms. And now we can use tree automata to process those trees in this way to define a natural class of functions on the space of programs. And you can also add randomness into it and random uncertainty into it, and have a post and less wrong, which talks about how to define an interesting compositional language for constructing this type of tree automata, which has strong connections to category theory, but I won't go into it right now. Okay, so that's just a bit about the Platonic side of the equation. Now, what's happening with the environment side of the equation? Okay, so in just normal kind of classical theory, we have Markov decision processes. So what's a Markov decision process? So we have some set of states S, we have some initial state S0, we have the transition kernel T, which is the mapping from S times the actions A to distributions over S. We have the reward function, which is a mapping from states to distribution over numbers, which are interpreted as rewards. And so, for example, maybe I have two actions A and B, I have two states S0 and S1, and if I'm at a 0, I take action A, then with probability 20%, I stay here, with probability 80%, I go here. But if I take action B, then with probability 60%, I stay here, and 40%, I go here, and so on. And what's important is this kind of framework assumes that I can observe the state. I know where the state is at every moment of time. So this is already not exactly kind of in sync with the cybernetic framework, the way I define it, because in the cybernetic framework, we're not observing the state, right? We're observing some state of observations. So this is, this could be good enough if we assume that the environment is Markovian with respect to the set of observations, but this is a super strong assumption that we don't want to make. So this is kind of a limitation of Markov decision processes. So usually the way we kind of try to overcome this limitation is say there is some state representation. So there is some function which maps histories of actions observations into the space of states. And if I know this function, then I can learn the transition kernel. But then the question is where this function comes from. How do we learn the state representation? And here, one thing that enters is something called regular decision processes. So RDPs. So what's a regular decision process? So that's by the way, a rather recent thing and still kind of obscure. I sort of kind of invented it myself and then discovered that other people have already done it. But and it's kind of surprised that it's that recent, but I mean there's reasons why it's a little complicated to work with those things, but they're still very interesting. So there's still some set of states S, but now there's an observation kernel which says given a state S in an action, what's the distribution over the observation going to be? And there's a transition function which says given a state, an action and an observation, what's the next state? And the notable part is that this thing is deterministic. There's no stochasticity here. For example, maybe my actions are A and B, observations are 0 and 1, and I have two states as 0 and as 1. And in this state, if I take action A, there's a 20% probability that I will get observation 1, and 80% I will get observation 0. But if I get 1, then I necessarily go here. If I get here 0, I necessarily go here. And so on. Yeah, Jones.
Very shortly, do you think when we design agents that have some form of world model, it would also be a good idea to split up the world model into parts like this, like something that predicts observations and something that kind of maps the dynamics of the environment?
You mean split it into this raw and T?
Yeah,
like this is
something similar to that. If we actually design an agent and design its basic architecture of its world model, should we split it up in a similar way?
Maybe. I mean, I think that like currently, okay, the way I'm looking at this is that those RDPs, they're kind of a toy model. They're kind of a convenient mathematical object to study learning algorithms for. Now, when you're going to kind of more, when you would try to do something more complicated, then you get the problem that the state space needs to be very big. Therefore, all the algorithms, all the naive algorithms, they're kind of intractable. But then you can try to say, okay, but we're going to look at RDPs, for example, that have some structure that can be exploited to do efficient algorithms, like the state space factors in some convenient ways and so on. So maybe in the end, we'll end up with something that's still literally an RDP, but having also some additional interesting structures in it that like are, for example, I wrote a short form about compositional tree MDPs, which shows how to build MDPs that have like spatial and temporal hierarchies in them. And you can like tractably solve the control problem. So yeah, I don't know, like maybe no, maybe we'll find out some different format, which would be better. But I'm just happy to have some mathematical object that I can start playing with and like prove things about.
Thanks.
Yeah, so notably, and by the way, both MDPs and RDPs have straightforward information version, right? If you just replace this delta by a box, instead of distributions, talk about infra distributions or here or whatever you see the symbol delta and just put a box in, you get the infra version of this, infra MDPs, infra RDPs, and so on. And okay, what's notable about RDPs is that when you're only looking at a control problem, like you only care about, like you know the RDP, you want to find a policy that maximizes expected utility, then you can just translate it to an MDP. You just consider what I denoted here T flat, which is the mapping from S times A to distributions over S, which works by composing those two. So like you use this raw, and then you sample this O, and then you use T, and once you done those two steps together, you get this T flat, and then you get an MDP, and you just solve the control problem for it. So from the perspective of control theory, this is just equivalent. But from the perspective of learning theory, this is genuinely a different type of model. Okay, And now
One quick question.
yeah.
How exactly are RDPs different from POMDPs? Like, I'm not entirely sure.
From POMDP.
What?
Yeah,
Yeah.
POMDPs. Yeah. This is a good question. So there is a substantial difference from POMDP. So RDPs are a special case of POMDPs, okay? But it's a very special case. Why is it so special? Because in RDP, the state is not directly observable, but it's indirectly observable. If you know the RDP you live in, and you see a sequence of action, observation, then you can calculate the state deterministically, because you just start with it as 0 and you apply t. So at every moment of time, you know exactly what the state is, if you know in which RDP you actually live. Okay? But in POMDPs, you don't know in which state you live. That's why in POMDPs, the control problem is p-space hard, but here it's also using linear programming like in MDPs. On the other hand, when you're looking at learning, then this is not equivalent to MDPs, because if you know the RDP, then you know the state. But if you don't know the RDP, then you don't know the state, you don't even know the state space. Okay? So they're kind of in between MDPs and POMDPs in some sense. So now, okay, symbolic RDP. So far we haven't been using this metacognitive thing at all. That's just been, usual stuff. Now the metacognitive part of the framework comes in. So what's a symbolic RDP? So let Q be some set of mappings from histories to programs. So every such mapping we can interpret as a program whose input is a history and output is a bit. And let gamma 0 be assignments from Q to 0, 1, like assignments from programs to values. So now a symbolic RDP is kind of the same definition as an RDP, except all of those mappings depend on an additional argument, which is gamma 0. So this means that the dynamics, everything that happens, can depend on the output of those programs. And the output of and those programs, they receive as input the history so far. It means that the dynamic is, strictly speaking, no longer Markovian, because it doesn't depend just on the state. It depends on the previous history through the implicit kind of dependence on the programs on the history. But from the perspective of the agent is not viewing those programs explicitly as some functions of history, but just as some black boxes that the agent can query.
Is
Okay.
gamma 0 basically the envelope from your very first slides?
The gamma 0 is kind of related to the envelope. I mean, the envelope is something I can use to make queries about gamma 0 or gamma more generally, right?
Yeah.
So for example, if I have complete Knightian uncertainty about those gamma 0s, then the symbolic RDP just translates into an infra RDP using those equations. And then you can just solve the infra RDP in the usual way. So again, the control theory here is just the usual control theory, but the learning theory is new because the key thing here is that this is not all programs. This is just some subset of programs. It's not computationally feasible to be running all the programs all the time, but there could be some set of programs, some small set of programs, which it is computationally feasible to be running all the time. So when you have a learning algorithm for symbolic RDPs, this learning algorithm is effectively learning which set of programs it would be convenient, it would be useful to run on the envelope, such that by running this set of programs, we have this model that can be used to obtain a particular level of reward. right? Which we would not be able to obtain without running those programs on the envelope, because then your actions could not depend on the actual programs. They can only depend on the state. So to kind of summarize what we did here, the classical thing is MDP, which assume a given state representation. When we also want to learn the state representation, we get an RDP. When we go to a symbolic RDP, we're also doing cognitive load balancing. So we're learning which set of programs it would be useful to run in order to use, those programs for making like predictions and taking actions. And this is a form of metacognition, where we're using a learning algorithm to learn an optimal cognitive load balancing. So the control theory of those objects is equivalent, but their learning theory is quite different. Okay. Okay, now let's talk about meta-reinforcement learning. So one of the motivations, not the only motivation, but one of the motivations for thinking about meta-reinforcement learning is planning in environments with traps. So traps is something which is kind of a notorious problem for classical approaches to like reinforcement learning and agency more generally. What are traps? Traps are transitions, events that happen and cause an irreversible transition, like irreversible transitions in the state of the environment. So formally, if the environment is described as some MDP, then there's a notion of communicating MDP, which means there are no traps. And if it's not communicating, then we have traps. So what does it mean for MDP to be communicating? It means for any pair of states, there is some policy that guarantees eventually getting from state A to state B. So in all the examples in the upper half of the slide are communicating. I can get from any state to any state I want. If I take the right sequence of actions, I can get anywhere I want. And for example, here I would need to wait until two things that only have a 10% probability of happening will happen in a row. Eventually it will happen. So it's still communicating. Eventually I will get there. On the other hand, in the examples in the bottom half of the slide, you have transitions which are completely irreversible. When I go from here to here, we can never go back. Or when I go from here to here, or when I go from here to here. So why are those things? So first of all, obviously the real world has traps, right? Like thermodynamics is kind of irreversible, and maybe some irreversible things we can kind of ignore and say they're not important, like we can kind of factor them out of our state representation or something, but they're definitely important irreversible things. For example, just to give a trivial example, if I'm training a robot and the robot decides to jump out of the window on the 5th floor and crashes down into splinters, then this is not something it can recover from. It's completely reversible. You cannot learn from your mistake and keep going unless you build a new robot, but it's like pretty expensive. And like if we're talking about transformative AI, then maybe you cannot build a new robot. Like if you killed all humans or whatever, then it's bad. Okay, so what's the difficulty with dealing with this theoretically? So when we have communicating Markov decision processes, then they're efficient learning algorithms in a weak sense. So by weak, I mean that those algorithms, like the classical algorithms, they're still going to scale, be polynomial in number of states and actions, which in realistic MDPs is going to be exponential. So it's a very weak notion of efficiency, but there's still some sense at least. This is not the problem we're talking about right now. So yeah, so in some sense, we have like efficient learning algorithms. And this actually implies that we can have approximate Bayes optimal planning in the gamma to 1 limit. So in the long time horizon limit, we have approximate Bayes optimal planning. Why? Because it's a trivial fact in reinforcement learning theory that if you have like algorithms with a sublinear regret bound, and as the planning horizon becomes longer and longer, this algorithm kind of becomes closer and closer to bias optimal. So we can approximate bias optimality. On the other hand, if we look at general MDPs, learning is definitionally impossible, right? Because like learning is defined to be like, you know, the definition of learning here is getting whatever expected reward we would be able to get if we knew the correct hypothesis in advance. So if you're like in a situation like this, and you need to choose between action A and B, like you cannot, like you have several hypotheses which assign different probabilities here. There's no way you can learn what the true probabilities are. You just have to do your, you know, best guess. You're not going to converge to the reward that in hindsight you would know is like the optimal reward. It's like even better than hindsight if you knew the full true hypothesis. So learning is just impossible by definition. But what's worse than that is that approximate bias optimality is NP hard in a strong sense, well, strong dual to this weak, right? So even if we allow our security parameter to include the number of states, number of actions, and the number of hypotheses in the prior, it's still going to be, and even if we make all the MDPs deterministic, just to make it life easier, still going to be NP hard. So, okay, so it's NP hard, so we have to do some kind of approximation, right? We cannot do something like approximation in the sense of not being close to optimal, but being far from optimal, but like the best we can in some sense. So, okay, how does it connect to what we were talking about before? So first, a short digression, partially observable Markov decision process. So POMDP. So POMDP, mentioned before, what is a POMDP? POMDP also has a set of states, but this time the state is not directly observable. Instead, we have some set of observation, which is the directly observable thing. And we have some distribution on what the initial state is. And there is a transition kernel which says, given a state and an action, what's the distribution over the next state and the observation we'll see. There's a reward function that given the observation, what's the reward? For example, we have like two states, observation 0, 1. Like, for example, I'm in state S0, I take action A. Then there's a 25% probability of C observation 0, stay in the same state. 25% to C observation 0, end up in a different state. 25% to C observation 1 and end up in this state, and so on. Here I take action B, I always see observation 1 and stay in the same state, and so on. For every state, I have a rule. What's the distribution going to be? So POMDPs are very nice. They kind of feel kind of much more general. I mean, you can always, they kind of in some sense feel more general than an MDP. So we'll see that we can also reduce them to an MDP. But important difference is what I mentioned before, the control problem is p-space hard. So it's much worse even than NP hard. It's p-space hard. And even just approximating the optimal value is already p-space hard. And that's why POMDPs are not very popular in like reinforcement learning theory. Although, of course, there are heuristic algorithms, like always. So now the connection comes. So how is it related? So before we were talking about bias optimal planning. So bias optimal planning can be reduced to the control problem of POMDP. How? Suppose we have some set of MDP hypotheses with a prior over them. Then we can build a POMDP where the new state space is going to be the product of the hypothesis space and the state space. The observations are going to be the state space. And we're going to have like an appropriate distribution over initial states is just the prior and, you know, choose the initial state Q0. Transition kernel is just saying, well, you know, whatever observation you saw here, this is actually should correspond to the state you ended up in. And the hypothesis never changes. If you started with a particular hypothesis, you're always stuck in the same hypothesis. Other than that, you have like the transition probabilities that come from the MDP for this particular hypothesis you're in, which is, again, part of your state now in the POMDP. So, for example, here we have two MDP hypotheses. One is assigned 60% probability, another 40% probability. And here's the corresponding POMDP. So now those two two states get two states here, those two states get different two states here, even though they are kind of the same states. But because the different hypotheses, we map them into different states. But our observation is only telling us whether we're in S0 or in S1. It's not telling us in which hypothesis we are. And now the prior corresponds to distribution over initial states. So we have a 60% probability of starting here, 40% probability of starting here. Now, solving the optimal policy for this POM-DP is equivalent to doing Bayes optimal planning for this prior. Okay. So, and now the thing is that we can also reduce any POM-DP to MDP. But of course, as you might guess from the fact that POM-DPs are intractable, but MDPs are kind of tractable, it comes with a huge price tag. So the way the reduction works is we construct the so-called belief MDP of the POM-DP. So what's the belief MDP? The belief MDP has as its state space the space of probability distributions over the original state space. So if the original state space was finite even, then our new state space is going to be infinite. For example, the original state space has like 4 points in it. Now we have all probability distributions over 4 points. So it's kind of this tetrahedron, or like more generally for a finite set, it's some kind of simplex, right? And now the initial state is just the initial distribution. And the transition kernel, well, it has this kind of scary looking formula, but what's actually going on here is that, you know, if we start at some theta, state theta, so it's a state from the POM-DP perspective, but a distribution from the MDP perspective, take action A, then we look what distribution we get from applying this action to this distribution using the MDP kernel. Then we sample an observation. So yeah, so right. So the POM-DP, so the POM-DP kernel, right? So the POM-DP gives us not just what the next state is, but what the next observation is. So we sample the next observation. Now we take the distribution we had and we condition it, we update it on the observation we had. And this is kind of our new state. Okay, so Bayes optimal planning reducible to POM-DP, POM-DP reducible to MDP. Composing those two together, Bayes optimal planning is reducible to MDP, but a huge MDP. What do we gain from all this? That huge MDPs for huge MDPs, we can approximate the control problem using infra-Bayesian coarsening. So what does it mean? So suppose we have our full state space S, and it's a really big state space, right? But we say, okay, this state space is really big, we cannot work with it. But let's cut it into pieces. Let's do some coarsening of it. Let's take some set S tilde and some mapping from S to S tilde. So this means that we kind of cut our big state space into pieces. And we say, okay, it's too expensive to actually keep track of this huge state space, but we're just gonna keep track of in which chunk we are every moment of time, not what's the exact status, but just which chunk it is. And this thing gives rise to an infra-MDP. So what's this infra-MDP? So the equation is here. So given a state in action, we like the transition infra-kernel maps it to the convex hull of all the kernels that we get for like any state S prime, which lies over this S. Any state is prime that's mapped to this S using this C. So in other words, if we look at this picture, then if I'm in this chunk, I'm looking at all the possible positions where the point inside the chunk might be, and looking to which distribution would the original kernel map it. So this point would be mapped to this distribution. This point would be mapped to this distribution. Then I'm taking the convex hull of all of this distribution, and I'm saying this entire chunk is mapped, and then of course I'm projecting them back with my coarsening, and I'm saying this chunk is mapped to this Creedle set that I got. And the nice thing about it is that this infra-MDP, which is like a law, this is a law that's satisfied by the ground. Like if this MDP is the ground truth satisfies the hypothesis, which is this infra-MDP. Means that if we follow the optimal policy for this infra-MDP, and for the infra-MDP, it guarantees some particular reward R, expected reward R, we're actually going to get at least that expected reward R in the full MDP. Of course, this is no longer equal to the optimum we could get from tracking the entire state space, but it is some guarantee that we can get. Of course, the next question is, okay, like, this is nice that we have this approximation, but where do we get this coarsening from, right? We might have like a lot of different ways to coarsen it, and we won't know which coarsening to use. And here the nice part comes in, that the fact that learning algorithms for infra-MDPs translate directly into algorithms for choosing a coarsening. Because the learning algorithm can treat this MDP as a kind of a black box that it can query and learn which infra-MDP hypothesis on the small state space it satisfies. So, okay, so how does it connect? So let's connect this to the metacognitive framework we started with. So let's suppose we have some prior, it can also be an infra prior, but here for simplicity, I use a Bayesian prior over what the environment is like. And we represent it symbolically. So symbolically, it means we represent it using programs that compute it. So formally, it means that we have some Z capital, which is a mapping from histories to mappings from observations to infinite sequences of programs. So what is going on here? So this infinite sequence of programs, we think of it as a single program. It's actually a single program that computes a real number. It just computes all the digits, the infinite sequence of the digits of the real number. So this object is basically a program that takes an observation and computes a real number. This whole object is basically a program that takes the history and computes a mapping from observations to real numbers. And this is precisely an environment, right? So this entire thing here is a program that computes an environment. In this environment, it is our prior in this case. So this is kind of the symbolic prior by the environment. Also have a Platonic prior, like a prior about gamma, which is like infra prior. It's an element of box gamma. And we can also notice that this Z can also be transformed into this psi1 of Z, which is a mapping from gamma times histories to mappings from O to 0, 1. So how does, so this is just kind of straightforward. The way this works is just once we have an element of gamma, we can evaluate all of those programs. And then, all of those things, they become just 0 or 1. This sequence becomes a real number, and this whole thing becomes the type signature here. So, okay, and then like, yeah, and then, okay, and here there's some technicality that here we got mapping from observations to 0, 1, whereas what we wanted is delta, we wanted them to sum to 1, but this is not a big deal because we can build into our prior here such assumptions that when composed with this, will always be guaranteed that we actually get a distribution here. Yeah, John?
Just to check, so this signature of Z, in principle, it could be simplified by removing the A and the O, right? Because I can swallow up the pair A and O into the star.
Yeah, but then, I mean, it would mean then a star would become a plus, like you need to have at least one A and O.
Oh, yes, you're right. But still, that looks simpler. So, is that
I mean, I wrote it that way because it was more suggestive in terms of the notation I was using before, right? Because before I had like mapping from this to delta O. So I wanted to show this analogy that kind of this thing here plays the role of delta O.
But can you again, maybe very shortly, tell the story behind this type? So what does it actually do? We have a history of action observations and another act.
Yeah, so this entire object is just a way to say that we have a program. I mean, it's kind of an under constrained way, but it's still a way to say that we have a program that takes this thing as an input and produces a list of real numbers pair observation as an output. Because if you look what is p to the omega, so p to the omega is just an infinite sequence of programs, but each program is a gadget that produces 0 or 1. So we have just a single program that computes like an infinite sequence of bits, which is the same as saying computes a number, a real number between 0 and 1. Then this single program can be regarded as such an infinite sequence, right? And then like if we have a vector of such programs, like one per observation, then such a vector corresponds to this thing, right? Or like if we have just a program that takes an observation and outputs a real number, then it corresponds to this thing. And then if we have a program that takes this entire thing as input and then produces like a vector of number per observation, then this corresponds to this entire type signature.
Okay, thank you.
Okay. So our full kind of metacognitive prior, meta prior would be the semi-direct product of this psi0, this psi1 of z, where kind of psi0 plays the role of the kind of Platonic mathematical knowledge that we talked about before. Psi1 z plays the role, but in terms of priors, right? This is just the prior. It's like our prior over like what the physics is. So for example, this prior could be like if we are actually trying to do Bayes optimal planing for a set of MDPs, this prior could be just literally a probabilistic mixture of MDPs. But it could also be something more complicated than that. So, okay, so what is it bias? So now we have a toy model. So just to simplify things, we make some very toyish assumptions, but that are going to like help us to understand what's going on. So first assumption is that there's a lot of times in advance of irreversible decisions. So before I start making irreversible decisions, I have a lot of time to sit and think like some kind of a Greek philosopher that just sits in their room and kind of thinks about, you know, the Platonic realms, like runs programs or with a computer or whatever. And when I say much time, it's kind of much time relatively to how much time it takes to actually sample this prior. So this is actual program, so it takes some time to run. Let's suppose that I have enough time in advance that I can run this program on many different inputs and see how it behaves. And the second assumption is that the zeta zero, this kind of Platonic prior, is decomposes into hypotheses, and each of those hypotheses corresponds to a good mixture of infra-RDPs. So what I mean good, what's a good mixture of infra-RDPs and what corresponds? So corresponds, I mean, when you combine this hypothesis with the zeta, right? When you kind of squash the two together, you can project it and get some actual environment. And I want this environment to be a good mixture of infra-RDPs. So by good mixture, I mean a mixture that's efficiently learnable. So for example, it could be that all the infra-MDPs are communicating, but it could also be that we are given some particular rule, which actions are safe to take, and then like all the infra-RDPs in this mixture satisfy that all the safe actions like don't lead to bad irreversible consequences. You know, all the actions that satisfy the rule also satisfy the rule. So this means that for such a mixture, I actually have an efficient learning algorithm that can learn which of the infra-MDPs is the correct one by following only the safe actions, right? So I don't have like traps in some sense, or whatever traps I have, I know in advance where they are. So these are like the two, but this is not an assumption about the real world. This is only an assumption about some hypothesis. And this hypothesis essentially plays the role of a coarsening, related to what we talked before about coarsenings, information coarsenings. So now, given those assumptions, the agent that I get can think of it as doing learning in two stages. One stage, the meta learning, when it just sits in its room and interacts with its envelope and learns things about its symbolic prior. And the second, the object learning, when it comes out into the actual world, it interacts with the environment. And here it's applying some learning algorithm for learning hypothesis about programs, some kind of active learning. Well, it's actually a reinforcement learning algorithm. We'll get to that. And here it's just using reinforcement learning on this good mixture of info MDPs that it got from the first stage. So to add some detail on that, so in reinforcement learning, the theory and also practice of reinforcement learning, we have different regimes, different types. So I listed 4 here: continuous, episodic, pure exploration, and simulation, where continuous simulation are the 2 most interesting for us. So they differ in terms of how do you do exploration versus exploitation. So in the continuous mode, we need to do exploration and exploitation simultaneously. And like we do kind of lifelong learning, and we immediately, like, there's no separation between training and deployment or anything. So those question marks, they kind of represent taking an action because I want to learn something, and this exclamation, which is called exploring, this exclamation mark kind of represent taking action because I want to earn a reward, which is called exploiting. So here I kind of need to think of both of those things as consideration, which action I take all the time, and all the actions I take, they influence the future, what's going to happen in the future. So, and then in the episodic regime, it's similar, only everything is divided into episodes such that there's no causal influence beyond the end of the episode. Everything resets when a new episode starts. And in pure exploration, everything is kind of divided into 2 segments. Here, I'm kind of only doing training, and here you can say that this is kind of training and this is deployment. It's kind of not online anymore. So, and kind of here in this phase, we're only doing exploration because we don't care which words we get in this phase. We only care about learning things for the benefit of the second phase. In the second phase, we want to actually start getting rewards. And then there's the simulation framework, which is similar to pure exploration in the sense we also have things divided into kind of training phase, which is kind of not the rewards there don't count for real, and the actual deployment phase where the rewards actually count. But here, the algorithm is interacting with a simulator of the true environment, so it can actually query the environment in any input. Like it can prepare any history it wants and query what will happen there. So it has this much more powerful queries where it can query any point it wants. So, okay. And the upshot is, why am I telling you this? Because the meta learning is basically a based simulation RL paradigm, whereas the object learning is based on continuous RL paradigm. Because in the meta learning, I'm not interacting with the environment, yes, I'm just learning things about my prior. So my prior, I regard my prior as a simulator of the environment. So here I can actually apply real, algorithms that exist and have like theoretical results about them for learning in this setting and get some guarantees. And here I can apply algorithms for continuous reinforcement learning with exploitation and get some guarantees. And when I put those things together, I get in this under this toy model assumption, some algorithm that has some nice guarantees. And the interesting thing about it is that we got some nice guarantees, despite the fact that our initial prior had traps, and it was NP hard to kind of do bias optimal planning for it. Could be a mixture of MDPs. It could even be a mixture of POMDPs, right? Because we only assume that we can efficiently sample the prior in order to do this simulation here. We don't assume that anything else. So a mixture of POMDPs can also work for this purpose. And this is already like gives us some kind of a toy model of some learning process with formal guarantees that is kind of inspired by this kind of metacognitive framework, and which is like not supported by classical approaches to reinforcement learning. And of course, this was kind of a toy model where everything is divided cleanly into 2 stages. In slightly more real life, meta learning and the object learning will have to happen in parallel, where the meta learning is kind of providing the prior for the object learning, because we don't have infinite time in advance to think about everything. But the object learning also provides something. It provides narrowing down the domain. So if I know that a particular history happened, then I don't need to study my prior in histories, which will never happen anymore. Not exactly true, because in the infra-Bayesian world, there might be causal influences, which give you reasons to study like counterfactuals. But aside from that, you can kind of assume. So we have this kind of closed loop meta-RL. Okay, and here, I think we should take a 5 minutes break. Or maybe I'll take Job's questions first.
Yeah, but I don't want to interfere with the break, so I can ask the question after the break.
Okay, so let's just do a 5 minutes break. Oh, okay, so the last part of the talk is recursive meta learning. And so what's the idea here? That before in meta reinforcement learning, we learned things about the Platonic realm that helped us learning things about the environment. But it was not really a closed loop, because learning things about the environment did not help that much learning things about the Platonic realm. Maybe you walk around in an environment and you find a computer which allows you to make cool calculations, and this helps you, but this is kind of a very slow feedback loop. Whereas inside the algorithm, you can have much quicker feedback loops. So the obvious question is, can we also talk about learning things about the Platonic realm, helping us to learn further things about the Platonic realm? We have this, that would be a genuine form of recursive self-improvement, because we actually have this kind of positive feedback loop going on, like algorithmic positive feedback loop. Okay, so first of all, quoting. So some notions. So what's quoting? So let H be like a meta hypothesis, just an element of box gamma. And let tau star, the element of gamma, be the ground truth. So the actual true outputs, which all the computation output, which of course the agent doesn't know, and nobody knows, because it's like uncomputable. And let omega small, an element of box omega capital, be the source of aleatory uncertainty. So what do I mean by that? So we're going to represent our hypothesis by computations. And our hypotheses are going to be contain randomness and also contain Knightian uncertainty. So to represent a hypothesis by computation, if you think of a computation kind of samples hypothesis, then it has to get random bits from somewhere, and it has to get Murphy's decision, like Knightian bits from somewhere. And this omega small will serve as the source kind of generator of this. So you can imagine it's kind of infinite sequence of random bits plus infinite sequence of Knightian bits, something like that. So now we can define a symbolic representation of H, like quoted H, as a mapping from omega times gamma to gamma, which satisfies the property that when we take this mapping and plug in the ground truth as the second argument, so we get a mapping just from omega to gamma, and now we use this mapping from omega to gamma to push forward small omega into gamma, the result is exactly H. So this is just a way of saying, this equation is just a way of saying that this thing is a computation that samples H. So let's look at it again. So this is the mapping from gamma to something. Therefore, we can regard it as a program, something that depends on the outputs of all programs. So it could be like just an actual program, and this is what the dependency is about. Also depends on omega, because this program also has access to the source of kind of coins in Knightian coins. And the thing that outputs is the domain of the hypothesis that we're sampling, right? So we're representing the hypothesis by a program that samples the hypothesis. And this program we're calling quoted H. So this is quotation. Now, reification. So reification is in some sense adjoined to quotation. I'm kind of hoping that it will be literally adjoined in category theory sense, but I haven't proved anything of the sort. So it's kind of an operator in the other direction. So suppose that eta is a mapping from omega times gamma to gamma. So it's some symbolic hypothesis, some program which samples some hypothesis. Then we can define omega shriek, element of box gamma, by the following equation. So omega shriek is going to be the set of all distributions theta, distributions over gamma, such that theta is an element of eta star applied to the semi-direct product of omega and theta. Notice this kind of a fixed pointy equation. So what is this thing? What is this reification operator? So this reification operator is basically saying, well, this eta is the symbolic representation of some hypothesis about, stuff, about like the computational world, but doesn't matter. So let's imagine it as a book. So a book is a symbolic representation, right? It's like has stuff written, which has some meaning that it represents. So this hypothesis eta shriek, asserting this hypothesis is basically pointing at the book and saying, whatever written in this book is true. So it's a kind of a roundabout way to assert the content of the symbolic hypothesis. I'm not saying what the content is, but I'm saying whatever content is encoded in those symbols, I assert, my hypothesis eta shriek asserts that it's true. And here the tricky part is because this book can also, so this book has stuff in it about gamma, right, about programs. But this book is also a program. So this book actually can have things about itself, can be self-referential. That's why we have this kind of self-referential thing happening here, where theta is an element of something that contains theta. And in fact, we need to use Kakutani's fixed point theorem to prove that this is a non-empty set. Okay, and now the last slide of our presentation. So now we get to actual we get to define recursive meta learning in our framework. So how do we define it? So we have some H represents the space of hypotheses, and chi is a mapping from H to box gamma, which maps like the label of each hypothesis to its actual manifestation as a numeric hypothesis, as a real set over gamma. Zeta is our prior over hypothesis. Psi 0 is just the push forward of zeta by chi, which is an element of, so the psi 0 we had before is equal to chi star zeta. And now we're going to have some condition. And the claim I'm making here is, if we have a prior, if an agent managed to somehow efficiently learn a prior, which satisfies this condition, and this is like a condition on the prior, then this agent is recursively meta-learning. Then this agent is able to use any knowledge it learns about programs, computations, to optimize its process of learning further knowledge about computation. So what is the condition? The condition says that for any hypothesis alpha in H, there exists some new alpha distribution over H, such that, first of all, new alpha is absolutely continuous in respect to the prior zeta. So if you don't know what absolutely continuous is, just imagine zeta is just a discrete distribution. So if zeta is just a discrete distribution with full support in H, then it can be just anything. Then this condition is just vacuums. The just condition that says that this thing does not like assign positive probabilities to things that the prior assigns 0 probability. So it's like consistent with the prior in some very big sense. The second condition, which is the real meat, says that if we apply chi star to new alpha, so we get some element of box gamma, this element is the intersection of two creedal sets. So it's basically the conjunction of two things. One thing is just the hypothesis alpha. The second thing, and here's the tricky part, is something which we quote and then reify. So what is this something? So we start with the prior zeta, then we look at this set. This set is the set of all hypotheses that are refinements of alpha. So all beta, such that the creedal set of beta is a subset of creedal set of alpha. These are hypotheses that kind of refine the hypothesis alpha. And we condition on our prior on those things. So the thing we get now is like, once we learned alpha and once we continue learning, it makes sense to do our learning based on this prior, right? The initial prior we started as, conditioned on the fact that now we already know the hypothesis alpha. So now we're going for refinements of alpha. And now we take this object, we quote it to make a symbolic representation of it, and we reify it. So by quoting and reifying it, we translate the assertion that the thing that we're learning is this prior to the language of programs in gamma. So it's the same language about which alpha has opinions. And now when we take the conjunction of those two, the knowledge that's inside alpha can help us learn it with a better algorithm. In the same sense that in the previous part, in the meta reinforcement learning part, we had like the knowledge of alpha helping us to learn things about the environment, right? Yeah, so someone comments, if I'm using Kekutani to establish existence fixed point, that doesn't imply anything about feasibility. So first of all, you're absolutely right. I have not proved anything about feasibility. It's the other way around. I'm saying if there is a feasible algorithm for learning a hypothesis class which satisfies this property, and this is like a big if, which I have no idea. Maybe there is, maybe there isn't. I don't know. This is like an open question at this stage. But if it exists, then this algorithm will have the property of recursive meta learning. And if it cannot exist, that would be an interesting, fascinating theorem in itself that to some extent rules out recursive meta learning. So, yeah, what's interesting about the Kakutani part is that the Kakutani theorem. So, what's interesting about this is kind of a technical remark, but it's kind of curious that usually when you use a fixed point theorem, the fixed point is not unique, and you have some arbitrary selection between fixed points. And then when in the computational world, this arbitrary selection is usually often intractable. Let's put it that way. But here, this does not really happen because this thing defines a unique object. There is no uniqueness issues because we're kind of looking at the set of all fixed points. And the kind of interesting thing here is because of the property of this thing, this set is actually convex, which is not usually the case for just usual applications of Kakutani. In this case, this set is convex, and because it's convex as a creedal set, so we have this unique object, which is this unique creedal set, which is defined by this fixed point condition. There's no arbitrary selection going on. And maybe this is like a huge super maybe this indicates something about good about computational feasibility, but like haven't really proved anything at all about it. So the way I imagine it is that if we had so I imagine that we're going to have some compositional language for describing hypotheses. For example, like the sort of compositional languages I talked about in my post. Like there's the categorical, there's the so-called string machines, and then there's the compositional MDP automata. But I think we're going to have some kind of a compositional language for describing hypotheses, which is selected for having like efficient learning algorithms. And here the thing is that if we can somehow make this language such that it contains an operation that allows like implementing this fixed point construction, if like this fixed point construction is one of the operations we're allowing in a language, and it still somehow allows efficient learning, then we would have nailed an example, like a constructive example of recursive meta learning. And this thing is, and like the upshot of this is that we get a genuine closed loop where mathematical knowledge is used to kind of improve the learning algorithm we use in some sense, and the learning algorithm is used to gain more mathematical knowledge in like this unlimited positive feedback loop, which is very similar to the kind of positive feedback loop that, for example, Yudkowsky talks about. But here it's in a much more concrete, rigorous framework. Yeah, and this is the end. So now I believe we have almost 30 minutes for more discussion and stuff. So yeah, feel free to ask questions, comments, or whatever. Yeah, Jobs?
Yeah, this is actually my question from on the first part. So I noticed you consider environments that might have traps, and even if you don't call them traps, that you might have environments which have kind of lock-ins where you make an irreversible decision at some point, and after having made that decision, you might still end up in a situation where there's aleatoric uncertainty. So let's say I can take a left turn, and that will give me either 0 or 1 reward in the end, maybe with equal probability, or I can take a right turn, and that will either give me -1 or 1.5, or -1 or 3, let's say. Yeah, also with equal probability. So now an expected utility maximizer would take turn B because it has a higher expected utility. However, I personally question very much this methodology in cases where there's no chance of repeating things, of things averaging out, as in a law of large numbers. And therefore, my question is, how much of your methodology actually depends on assuming an expected utility maximizer? Would much of this also work with at least some other forms of decision rules that would maybe rather do a worst case analysis in this type of situation?
Yeah, that's an interesting question. So actually, worst case analysis is the thing that's super easy for me to do with my framework, because it's kind of inherent in Bayesianism. So if you want to do worst case analysis, you just replace kind of the distribution by a Knightian uncertainty, and then you're doing
that's different. Okay, I see that there is some element of taking the maximum in your framework, but in the situation I described, wouldn't your analysis? I mean, I describe a situation where you are perfectly sure about the aleatoric uncertainty. You see the two coins being tossed when you take a left or take a right. There's no Knightian uncertainty about that. So it's a clear probability distribution. Would you still advise modeling that with kind of Knightian uncertainty in order to be allowed to take the maximum?
Yeah, yeah, I don't know. Like you could you could do all sorts of things. Like you could introduce some latent variable in which the utility function depends, and then like effectively and then like have Knightian uncertainty about that variable, and then like effectively you have like a minimum over multiple utility functions. So there's like one thing you could do, and yeah, I know this specific example of like yeah, I would need to think about it. Like I usually just kind of you know, my kind of usual approach is to get interesting results under some halfway plausible assumptions and not kind of hurry to generalize my assumptions. So I usually kind of don't go in this kind of direction. But like, I don't know, maybe if I had like 10 minutes to think about it, I would have like some some way how you can do the thing you want to do in my framework.
Thanks.
I don't know.
Thank you.
Could you give some very concrete example for the bipartite cybernetic framework thing, where like how would it look like if this AGI box would use the envelope, or could you describe sort of a particular problem that the AI tries to solve in the real world, and then like how it would interact with the envelope in order to like get useful cognition out or something like that?
A concrete problem. So I mean, I kind of had like two meta concrete problems because, well, it's a meta talk, so everything has to be meta. I mean, kind of my meta concrete problems were like the symbolic RDP and the meta learning and the thing, right? But like you can imagine examples of each, like yeah, like a simple. I mean, I would have to like use my imagination to come up with some like super concrete example, but you can like easily imagine things where like, so the symbolic RDP allows you to deal with situations where you cannot evaluate all the hypotheses simultaneously, right? Like you have some hypothesis space, you like implicitly have some hypothesis space which you want to be able to learn any hypothesis from it.
That is about describing the world, the hypothesis space.
Yeah, about like the actual world, about the environment. But you're not able to evaluate all of them because like there's each of them has involves some expensive program that you need to run. So you cannot evaluate all of them simultaneously. You cannot be like continuously evaluating all of them. And like in classical approaches, you need to be continuously evaluating all of them because I don't know, if you want to do Thompson sampling, then you need to kind of update your beliefs, and then you need to like evaluate each one of your beliefs to compute its likelihood or something like that. But if you're working with like symbolic RDPs, then your learning algorithm is doing the work of like sometimes querying one program, sometimes querying a different program, and eventually kind of converging to, okay, this is like the actual set of programs that are interesting, that are actually like predicting something correct about the world, right? It's like, you know, it's like I'm trying to discover physics, and I want to write down some equations based on physics that will help me to predict the world and to make good decisions. So like what this buys me is instead of having to kind of simulate all possible equations and see what they do all the time, I can somehow play with one equation, play with another equation, and in the end kind of converge to, okay, this is the equation that's actually useful. So now I actually need to like keep simulating this equation. I don't need to keep simulating all of them. So it's like a form of resource kind of a form of load balancing, which allows your algorithm to be much more efficient.
So in this example, the envelope would basically sort of be the thing where, like in some sense, I don't know, or like I guess maybe this I misunderstood. Like, okay, like if we had like Solomonov induction, then you could think of, in the envelope, I sort of run all of the hypotheses, all of the computable programs. And now we're not doing that, but we're doing sort of an approximation of that, where the core thing of the system queries based on some learned, like it learns what it should sort of query from these hypotheses that are then run on the envelope and then get results back to like approximate something like that.
Yeah. And like in the second, so that's like was the first example. In the second example of meta reinforcement learning, there we're using the envelope to combat the fact that we have like some prior over the real world, which is that we kind of use it to combat the fact that Bayesian planning is intractable, right? So kind of Bayesian planning in the real world is intractable. That's kind of a fact of life. And kind of classical reinforcement learning theory just ignores it by kind of positing that let's just assume either that there are no traps, or that we can just do everything in episodes magically, right? So it kind of just avoids the question. Whereas
So
I'm saying,
with Bayesian planning, do you mean something like we take every hypothesis that we have in our prior, and then, I have some sort of estimation of what's the current world state, and we apply each hypothesis to that to generate sort of leaf nodes, if we're thinking about as a tree, and then for each of the leaf nodes, we generate it again, like an infinite number of nodes, and we do that until we find some state that's desirable or something.
So Bayesian planning means we're looking for the Bayesian optimal policy. So yeah, like if you were doing it brute force, then you would kind of build this tree, which would be like exponentially large and completely intractable, right? But there are situations in which it is tractable to find a Bayes optimal policy, or to approximate Bayes optimal policy, right? Like for example, when we have like a mixture of communicating MPP, then it's tractable to approximate a Bayes optimal policy. But in general case, it's intractable. And here what the envelope does is, the envelope, you just use it to do kind of mathematical experiments that you learn from in order to figure out what's like the best approximation that you can use to do approximate Bayes optimal plan, approximate Bayes planning.
Yeah. Could you maybe describe what this would look like if I have the task of move a banana from bin A to bin B? What would you do?
I mean, if you want to move a banana from bin A to bin B, but there's also a crocodile which can eat you, right, along the way, and you're like, okay, I have a hypothesis that the crocodile is hiding in the bushes, but like I have a different hypothesis that the crocodile is actually hiding in that box over there, right? And I want to like come up with a plan which would give me the best probability of success, given that I can end up, being eaten by the crocodile. And there's like this exponentially large tree of things that can happen with, me running between different points and the crocodile chasing me and whatnot. And I'm trying to like come up with some approximation that will, allow me to come up with the best plan I can. Then, I start from, then what I'm doing is I start from building a simulation in my head of this whole like system according to the beliefs I have, and I play with the simulation. I mean, when I play on it, I actually apply a learning algorithm to it. By applying a learning algorithm to it, I kind of construct some course model, a model which is not as good as the simulation, but coarser, but which has the property that for which I can solve the Bayes optimal planning. And okay, cool, I have some approximation that I know how to do.
But how would you generate this? Because right now, when you describe it like this, it sounds like sort of if you are the like core of the AGI, then you would generate this algorithm and then you give it to the envelope to run it. But then sort of, okay, in that case, does that mean that the meta learning of like generating the new cognitive algorithm happens in the core and not the envelope?
The meta learning happens in the, the meta learning happens in both. I mean, the core is running the learning algorithm itself, but then every time it needs to, but sometimes the learning algorithm tells it query the envelope with such and such input, and then it has to go and query the envelope, right?
Yeah.
I mean, and that's again, that's like a simplified, that's kind of two-stage thing. It's in real life, it's not really two-stage. It's like I'm doing it it's not like in real life, I don't have like, okay, I sit with a simulation, figure out my plan for the rest of my life, and this is the end. Like, no, you have to like continuously, like, because you have only finite time to think about things, you kind of continuously keep thinking and refining your plans, right? So like, you came up with something, you started working on some plan, then you had more time to think, you did more experiments with your envelope, discovered some better model, and now you switch to the better plan, right?
So would one use of the envelope be that you basically, like you said, you generate some simulation of the environment and then maybe a coarse-grained version of it, and then you run that on the envelope, and then you do science on that thing, such as that you figure out and understand it, such that then you can generate a world model, I guess, that is now that maybe there are 3 world models. I'm not sure.
I mean, there's like the original prior you started with, and then there's like the model that you kind of learned in the process. Yeah, but like yeah, but then those 2 cases, they're just those 2 use cases I gave. They're just kind of 2 toy models. In the real world, you have everything happening together, because like maybe the model that you actually learned is a symbolic RDP, and so when you're actually executing the plan, you're also using the envelope in some different way to make some queries, you know, because to compute things. So all of those things, they happen together. Yeah, Jobs has another question.
Yeah, sorry for asking so many questions, but I was reminded a little bit, just a little bit, of a plan that I think Tamsin Lee, if I pronounced it correctly, from Orthogonal has put forward, which is kind of, if I understood it correctly, first having kind of a very powerful AI try to figure out what the kind of the text, the alignment, AI alignment 101 textbook from the future would contain, and let it do that for some while. And once it's figured out what the perfect alignment plan is, then implement that plan, which seems like a little bit similar in the sense that we're first doing a lot of simulation, not acting in the real world, forming a lot of hypotheses and so on. Is that, would you say it's related or not?
Maybe I haven't thought about this connection at all. I don't know. It could be related, but like in my mind, I'm talking about something much more general. Like maybe that thing is kind of could be regarded as a special case or something. But you know, I'm thinking about it just in terms of like absolutely general theory of agents. You know, how to understand agents that kind of go around the world and think about stuff. And like I said, the model where you do all this simulation up front, that's just like a simplified toy model that was used just to kind of explain that you can get something from this whole framework. The real world, you would, you know, the real world is the real world. Sometimes you sit in your room and you think, and sometimes you go out and you do things, and you alternate between the 2 and so on. Yeah, there's the question by Clement.
Yes, hello. How do you plan to use this model to like deal with alignment problem questions? Like, because so it's very theoretical, and so do you plan to make proofs on the agent's behavior in this context or things like that? Like, how do you plan to use it?
Yeah, so I mean, this particular research direction is kind of one of many research directions within the broader context of my research program, which is called the Learning Theoretic Agenda. And the goal of the Learning Theoretic Agenda is to come up with a mathematical theory of agency. So like understand foundational questions about agents, where like the assumption is it's not necessarily that every particular single question, like we can probably find connections between many of those questions, specific things about alignment, but like the general methodology is not thinking about alignment all the time, but just trying to figure out what is this thing called intelligent agents and what properties does it have. And once we have this theory, then we can kind of use it as a toolbox to build systems about which we can prove they're aligned, or at least we can conjecture that they are aligned, where the conjecture would be kind of well supported by some theoretical arguments. And in addition to this, I also have like a concrete proposal for like a sketch of like a proposal how to align system called physicalist superimitation, which is based on a framework called information physicalism, which is part of the research program. And the information physicalism framework is based actually on this metacognitive framework that I talked about now. So it's kind of all related, but it's like just more like one of the building blocks in the big picture. Right. So,
Okay, thank you.
yeah, and Ali?
So one thing I'm a little confused by is that you said that humans seem like they have metacognition, and I'm struggling to figure out how to describe a human in this framework. It doesn't seem like for instance, the envelope, you said that it uses more resources than the agent does, so the agent can't feasibly simulate what's going on in the envelope. That doesn't seem like a description. Like you had this little cartoon drawing of a person thinking earlier, and presumably when they're thinking, that's supposed to be something like running a query on the envelope. But I don't get how that can be the case if, like, you know, the system 2 thinking is not really, that's the part of our thinking which is very not expensive, right? All of the expensive stuff is like the system 1 stuff. And I'm just kind of a bit confused about that envelope core. How does that map into a human?
Yeah, this is a pretty good question, I think. So the answer is, okay, so the first meta answer is, since we're in the meta business, the answer is that I'm really not an expert on brain science by any means. So everything I think about is just wild speculation, might be just completely kind of off the mark or only kind of vaguely in the direction. Like I would be actually happy if someone who actually knows brain science would think about, you know, how to connect brain science to this kind of models. But now, like, the object level answer is that my suspicion, which is again speculation, is that in humans you kind of have like the thing that corresponds to the envelope and the thing that corresponds to the core, they probably have like different computational advantages. Like maybe like the core is better at massively parallel computations, and the envelope is in some sense better at serial computations, because kind of conscious thinking, well, because the brain as a whole is obviously massively parallel, but also conscious thinking has some kind of seriality to it. Feels like, you know, the thinking about things thoughts can follow in some serial order. So perhaps what happens in the brain is that the envelope has only an advantage along some very particular dimensions. And again, my speculation is that this is kind of this property of human brains, which is kind of some accident of evolution, is also the reason why human metacognition is fundamentally limited. So humans are obviously unable of arbitrary self-improvement in a very strong sense. Like we're very far from being able to you know, do arbitrary self-improvements. We cannot, like, you know, run something similar to our brain inside like our thoughts and then like tweak things in it and make it better. Like we're nowhere near that. So I think that actual humans have metacognition, but it's kind of like in the space of all possible metacognitions, it's some kind of very weak form. Whereas AIs could have much more powerful versions of metacognition. And this is also might be a reason for concern, because that could also mean that AIs can have like, you know, things that behave like so-called fast takeoffs, because usually it is much more powerful metacognition. This is my kind of speculation.
Thank you. Could I ask another question, or should I?
Yeah, sure.
Oh, okay. So the reason I was asking about mapping a human onto this framework is that I'm kind of worried about stuff like Stuart Armstrong's Occam's razor is not enough to, what was it, infer human values, that kind of thing, where it seems like you need some kind of additional model of rationality of humans in order to figure out what they value. And kind of what I was hoping for, a theory of agency, in a sense, is something that like you could point to and say, okay, if you can have such and such kinds of approximations to this, which are quite natural, and humans seem like they fit this natural approximation of the theory of learning or the theory of agency.
Mhm.
And therefore we have some sort of model of how they can be irrational. And then you can feed that into the agent, and then you can reasonably infer human values. Do you feel like your agenda would be able to provide something like that? Or is that not something that you would like to get out of it?
Yeah, that's an excellent question. And in fact, I was going to talk about this topic exactly, but it was too much because the presentation was extremely long as it is. So I believe that specifically metacognition also gives us some advance in that precise direction, because like you said, one of the issues is that, like, if we want to kind of infer values from a policy, then there are ambiguities, because like you can interpret the same policy as optimizing different reward function. But if you switch from the cybernetic framework to the bipartite framework, where like the policy is not only talking about external actions, but also kind of internal actions, like queries to the envelope, then you have much more information. And in fact, you can check what the agent would do in counterfactual mathematical worlds, and not just in counterfactual physical worlds. And essentially, this allows you to test what the agent would do, assuming different beliefs it could have about the world. And then it provably gives you much, much less ambiguity in determining what the utility function is. So my answer is yes, I definitely want to do the kind of thing you were talking about. And the Metacognitive framework is one piece in the puzzle of how to get there.
Thank you.
Yeah, Jonas?
Is the main problem with human metacognition not that you just can't, like, if we would figure out neuroscience, which, like, I mean, if the AI doesn't kill us and if we just keep trying, we could probably just figure it out, then we could do arbitrary self-improvement, right?
If we could figure out neuroscience, we could do arbitrary self-improvement. I mean, kind of, yeah, but like, I mean, this is sort of like okay, if we go back to this kind of picture with the agent, right, connected to the environment, then if the agent did not actually have an envelope, but it would just, or like it had an envelope, but it was like a very weak one, and it would be walking on the street and it found this much stronger computer, right? Then the agent could go, oh, cool, this is like a strong computer, I could use that. Then it could eventually learn to effectively use this computer as like an extended envelope or something like that. So, so it's true you can kind of compensate by on your kind of lack of metacognitive abilities by kind of building a sort of exobrain. And yeah, this is super true, but this is kind of a limitation, because if you don't start out with a good brain from the beginning, then your kind of build-up curve, your kind of the time it takes you to do this thing, and like the speed of the feedback loops and everything is much slower. So in terms of qualitatively, asymptotically, you might be able to kind of do the same things in some sense, but in practice, you would have like you would have to like work harder and for a longer time in order to get there.
Yeah, I guess I was just thinking that, like, a mouse, probably, if you, like, no matter how long you leave a mouse, they won't like be able to self-modify, because like they wouldn't do science and try to figure stuff out. But if you like, and the limitation in the human seems more like that you don't have the correct access to your cognition, and not that the human cognition couldn't reason about human cognition, but more like that it's like opaque. It's like locked away.
I mean, it is opaque, you're right, but also, I mean, you're right, it is opaque, but also you cannot really run an emulated brain inside your brain by a conscious decision of it, right? So even if you kind of knew what
But I can do something close to that. Like if I imagine some person that I know really well, I can imagine what would they say.
Yeah, kind of, but you cannot say, okay, let's tweak this person and give them a better learning algorithm and now see what happens, and like have them figure out, have this new person figure out something that you are not smart enough to figure out on your own. Like,
Yeah, you can't do that. I have another question. If nobody else has another question.
Yeah, I think that Mikhail has a question. Mikhail?
Yeah, I asked it in the chat. So is there a way for the agent, for the part that queries the envelope and takes actions to self-modify?
So is there a way for the part that queries the envelope and take action to be allowed to be changed by the agent? Yeah, I mean, so the answer is no. Like the core is immutable. I mean, if it was kind of mutable, then you could also, the agent could kind of damage itself irretrievably and not be able to recover from that. So it's kind of a limited form of self-modification because there is an immutable part, but the fact there is a mutable part is not a strong limitation in practice, because you can just kind of, like in principle at least, you can in the envelope run an emulation of a new and improved core and kind of route everything for it eventually, if you decided that's a good idea, like subject to computational constraints eventually. But in some sense, in terms of kind of qualitative asymptotic performance, the immutability of the core shouldn't really matter. But it does matter in terms of being able to prove some guarantees, because if you were a learning algorithm that could just had no protection at all against modifying yourself, then you would just accidentally damage yourself irreparably, and you wouldn't converge to anything good. Yeah.
So like, is it a good model for an AGI? Like if you expect that, well, like you can't really just like run an agent in the envelope and like bit by bit just copy its actions, because like if you think that it's not actually the optimal thing to do that, then you wouldn't do that. But like you can imagine that AGI would indeed just like self-modify in some ways, and so like guarantees might break if like it's like a descriptive model.
So you're asking what happens in a real AGI that can find some way to hack into itself and modify its core, which is not supposed to be modifiable, right? Did I understand the question correctly?
No, like to what extent is it something that can be descriptive of like real AGI systems? I
mean, I think it can totally be descriptive. I mean, why wouldn't it be? I mean, yeah, I don't know so like I think that AGI systems, in my opinion, have to implement some version of this metacognitive thing. That's my opinion.
Yeah, but would it be restricted to only like running something in the envelope? Like it seems that like in the real world, it's easy to expect that they will self-modify like in any way, like if they expect that this is for some reason good.
So eventually the agent can find some way to self-modify through taking actions in the environment, but you don't want it. I mean, just from a capability point of view, you don't want to just give it immediate unrestricted access to that. Like eventually it can do it, and then it would be able to irreparably damage itself, but then this is just a form of trap, right? So this is something that it can, so, you know, if that's like something that's part of its prior, then in kind of the meta learning part, where it's kind of imagining different things that could happen, it would also consider scenarios like hacking into yourself. in changing yourself in various fine ways. And some of those would be bad and some of those would be good. And eventually it would figure out what's, the best way to go about it in expectation. So there's no like contradiction between this model and the fact that in the real physical world you can modify yourself, but it's kind of important that like it's important that you can, well, that you can you don't have to modify yourself, right? You can just sit in a box and think before you start doing things.
Can I give a quick counter argument for why I think this might be incorrect? And like the thing that you said about that you need a system to have this, like metacognition, or like how I would think about metacognition is about you want to figure out certain algorithms that you can use to reason well about the world. Like, for example, you could think about, I want to find the algorithms that allow me to access the most states or whatever in the future, if you want to have a general thing that's not dependent on any objective. Or you can think of, I want to have algorithms that fulfill this objective very well. So metacognition is always about figuring out certain algorithms. Now, if we would, let's say we want to do a pivotal act, then we're gonna have some task, like, I don't know, let's burn all GPUs or upload the human or whatever. And if we would have a metacognitive algorithm, that would successfully eventually be able to perform the task, then that will mean it will have found certain kinds of algorithms that are good for reasoning about the world in the ways that allows it to make a plan for executing its actual task. Now, if you could just figure out all of these algorithms directly, we would need a metacognition.
You cannot figure them out directly because the AI is smarter than you and the algorithms are extremely complicated and tailored to a lot and depend on a lot of like specifics, like the AI specific computational abilities, for example, and even actual things in the physical world. So yeah, you just can't. But I think Valeria has a question and hasn't yet had a chance to ask any questions. So I think I'll give the microphone to Valeria.
Yes, yeah, I wanted to ask you why did you choose the representation of NDP as a basis for the for studying the self-improvement and the meta-learning? Is this a choice making the more realistic the type of traps the AI can fall into?
So why did I choose to use MDPs? So MDPs are just a convenient mathematical tool that we know how to prove things about. We have we understand the control theory of MDPs and we understand the learning theories of MDPs. So that's why, yeah, I mean, and they're like a pretty natural mathematical object. So that's why I guess I use them as a starting point, but maybe I missed something about your question, but I think that's.
So yeah, I'm interested in the, do you think that the traps that you, as they are in the theory of MDP, then they correspond, they would correspond to traps in which the AI can fall into through his decisions.
I mean, in the real world, it is a fact of life that a lot of things are irreversible, right? Like, jumping out of the window is irreversible, but even simpler things like saying someone a thing, you cannot unsay once you said something, right? That's also a simple example of something that's irreversible. Life is full of irreversible actions, and you need to somehow navigate that. And we need to somehow, but we know from theory that in the presence of irreversible things, bias planning gets intractable. So we need to use some kind of approximation algorithm. And what I show here is that that such an approximation algorithm can flow out naturally from a process of meta learning in a metacognitive framework. And I think this is a fascinating observation. And once you've installed this metacognitive framework, you automatically kind of get this this type of approximations for free. Your agent is kind of learning on its own how to do those approximations.
Right, thank you.
Ali, you have another question? Ali?
Sorry, I'll skip my question.
Oh, you're still raising your hand. Okay, fine, cool. So I guess we're back to Johannes, right?
Yes, I would like you, if you can, to what is the generator for you think these algorithms we would need to figure out for pivot like are too hard to figure out?
Why are those algorithms too hard to figure out? Because, okay, there's like a range of reasons. So first of all, in real life, algorithms are like non-trivial. Like you have a lot of problems for which people come up with more and more and more, like better and better and better, but more and more complicated algorithms without some end in sight. So it's like, seems that like it's not a realistic task to just figure out the perfect algorithm for a thing. So it feels like a system that can come up on its own with new and better algorithms would always have the upper hand over a system that's just been hard-coded to stop at a particular algorithm. That's like one thing. Another thing is that your AI is running on some very particular, very specific hardware, which has very specific computational properties. And for this particular hardware, there's going to be some very specific algorithm that's going to be optimal for using its resources in the best way. And because like the peculiarities of the hardware are likely to be quite complex, then the algorithm is also likely to be quite complex. I mean, it's like, you know, it's like, okay, another example from real life is you look at code optimization, right? We look at code that has been optimized. Optimizing code is a highly non-trivial task. You know, programmers spend a lot of time and come up with all sorts of crazy and very non-trivial tricks how to, you know, we need to write this register before that because then the cache will do something. Like it's a super non-trivial task. It's not some bounded task. We want to just find the perfect solution and stop there. So that's like another like real life example. And I mean, more generally, if you include things like cognitive, like load balancing, it feels like my notion of metacognition includes things like load balancing. I feel like without load balancing, your whatever you do is going to be very inefficient because maybe you have an algorithm for learning the best model of the world, but it doesn't have like a load balancing built into it, then it's going to be much less efficient than it could be, and to an extent it might make it completely intractable. And like, okay, if we go to the meta reinforcement learning example, then it would be like, okay, I want to find by hand, like, you know, you want what you're saying would amount to, instead of having the AI learn some approximation of the prior, which is tractable, we will find ourselves some approximation of the prior, which is tractable. But then also this approximation is not enough to find it one time in advance. You need to continuously update it as you continue to update your prior. So obviously that's not something that's feasible to do. That's kind of like the fact that you need to search, the fact that you need to do some kind of approximate bias optimal planning, that's just a fact of life with which you need to deal somehow. So you could try to come up with a different way to deal with it, but I'm not sure why would this different way would be better. Like you need to do something. Like it's not a problem. It's gonna go away by itself. And
would load balancing, let's say in the terms of when you build, so load balancing, let's say in the case where we built a model of the world, would be about, or like if you do this approximation of Solomonov induction, I guess then it was about you figure out what are the important things such that you can sort of ignore all of the unimportant hypotheses and don't even compute them. That's what you mean with load balancing, right?
sort of, yeah. You kind of have a hypothesis space where you cannot evaluate all the hypotheses all the time. So you need to decide how to query just some of them. Another reason why I think metacognitive it has to be important is because I think that humans are using metacognition, and metacognition is really important for humans, and it kind of and it seems to me kind of hard to believe that this is a part that you can just throw out and still get something which is like superhuman very easily, at least. I don't know. I mean, you can always kind of try to do this kind of trade-off. I mean, we could also say, let's don't build AI at all. Forget about AI. Let's just figure out how to build a global system that will prevent bad actors from building unaligned AI forever. Using whatever you want to use, up to non-attack and upwards. We could formulate the problem in this way. The reason we're not like relying on this kind of solution to the problem is because we believe the problem is really, really hard and actually needs like superhuman AI to solve it in time. And if the problem is hard and needs superhuman AI, then I am kind of skeptical about being able to kind of scheme on and I'm kind of skeptical about some kind of dumbed down AI being good enough for the purpose. Yes.
Yeah, I mean, I guess I agree that this could be a problem, but I'm not sure that it is. I can like go on forever, and if nobody answers the question.
I mean, I cannot prove that this is the case, but this is my intuition. I try to give some generators for this intuition, but this is like
yeah.
Not,
Thank you.
Okay, I think Morgan has a question.
Yeah. This is an interesting talk. I something I'm wondering about is, are you like, have you been trying to at all like think about like how to quantify or at least characterize like to what extent like an agent is being metacognitive versus like just sort of like running a hard-coded algorithm? And sort of like my motivation behind this is like, okay, so like you observe that like sort of like as an agent gets smarter, like it seemed to like be more metacognitive, like, or at least like smarter relative to like the algorithm that like its designer. Like, so like if you look at like beavers or spexes or bees, like, they just sort of like, they do like intelligent things because they're like running this hard-coded algorithm, but like metacognition is like not useful for them because like they could not come up with an algorithm that's better than the algorithm that they're doing. Whereas like humans have like some metacognition, like because we're able to like think of things that are like better than like what evolution could come up with. And like, an AGI, I would think would like be even more metacognitive because like it's well, first of all, there's the whole like, being able to modify its own source code and like being able to like just having more avenues for that, but also just in virtue of being smarter, it like has more potential to like possibly come up with like better algorithms for what it's doing. And then like the other thing I was thinking about is like, I mean, to some degree, like metacognition like might be a thing, you know, if we could like make an AI like not be less metacognitive, like that might be a good thing, because then it wouldn't like do this like self-improvement stuff that you know, could lead to trouble. I don't know. Just half-baked things I was thinking about. So I don't know, have you thought about these sorts of things, or like talking about like to what extent an agent is being metacognitive versus just sort of implementing an algorithm?
I mean, it's I mean, kind of related to the thing I said before, with humans having some limited form of metacognition. It seems like you could have like a kind of something akin to the bipartite model, but with different computational like constraints on the envelope and on the setup, and it would kind of give you different levels of metacognitivity. I don't know, I'm not sure it really translates to kind of a linear scale of more or less, or maybe it's something more complicated than that. But there's definitely something like that going on. But yeah, but I mean, my focus at the moment is just kind of figuring out math, right? And then kind of thing. So about the thing you said with AGI, I mean, yeah, it's like, I mean, it's like what I said to Johannes, like maybe you could make an AI that's not metacognitive, and then it would be less dangerous, but then also maybe it would not be useful for you know, solving, for, you know, doing pivotal act or whatever, solving the constructing this safety net that we want the AI to give us. So yeah, I don't know.
Thanks.
Okay, and Aline, do you have another question?
Yes, yes. So I guess two technically. One, to what extent is it important that groups like ARC develop tests for metacognition so that we can kind of see if agents we're building are developing these capabilities? Because as Morgan said, they do seem quite worrying. And two, to what extent do current algorithms already have metacognition? Because like, I probably wouldn't say GPT-4 has metacognition, but then again, if you do ask it to reflect on itself, it does seem to be able to improve its reasoning, but like that's to a very minor degree. So yeah, those are my two questions.
So I think so the second question was, to what extent do existing algorithms already have metacognition? And the first, I think I didn't manage to make out the first question. So can you repeat it?
So how important is it that we have tests for metacognition in things like ARC evals? Right, because like ARC did some evaluations of GPT-4 before they released it, and I assume that more groups are going to continue doing evaluation of bigger and better AIs. So how important is it that we start developing now tests for metacognition, or is that just not really feasible?
I do not. I think that current AIs don't have metacognition, in my opinion. I don't want anyone to develop AIs with metacognition, because I think that would be bringing us way closer to the disaster we're trying to avoid. My focus is purely theoretical on like understanding the theory of this in other aspects of intelligence, until we reach the point where we have such a good understanding of the theory that we can actually build an AI that's also going to be aligned. And as much as possible, I would rather avoid, I mean, there's probably no harm in experimenting with systems that someone already built, you know, unless those experiments somehow lead to capability breakthroughs. But I'm very much on the side of, let's not advance capabilities until we know what we're doing. So this kind of thinking was very much not in the direction of, oh, let's build an AI with metacognition. No, it
So
was just
I mean, I don't think I said that. I was asking like, how do we test systems that people build for metacognition so we can raise a warning
Oh,
flag?
how
Or is
do
that
we
in and of
test?
itself dangerous?
Yeah, how do we test? I mean, how do we test is an interesting question. I think we can, I haven't really thought about it, but I believe that, you know, based on the examples, even in this talk, I could probably come up with some benchmarks such that I would say, well, if a system passes those benchmarks, that it has some kind of metacognition in it, maybe, you know, like the kind of tasks that I was thinking of here. So, you know, I don't have like off the cuff answer, but you know,
Okay, but
based on those.
if I went over the talk carefully, do you think I would probably be able to generate such benchmarks? Or is that something like I'd need a lot more experience with? Because I'm kind of interested in, you know, making benchmarks for systems, but
If you could you make, I mean, I'm not sure. I mean, this is something that requires thought because it could be like a double-edged sword. I mean, on the one hand, if we discover that existing systems have metacognition, that could be kind of a warning light, and in this sense, it's good. On the other hand, once you create a benchmark that existing systems don't pass, that kind of incentivizes capability researchers to build some new thing which passes the benchmark.
yeah,
So
so
that's why-
ideally these benchmarks wouldn't be public. They would maybe say be private to ARC, and then whatever they're doing, it seems like a black box from the perspective of
Yeah.
capability.
Yeah, you're right. Yeah, you're right. Yeah, I don't know. I mean, that's. I mean, if you want to do something about this, then we can kind of discuss it later. I mean, I think this is.
Thank you very much.
Yeah.
I do want to flag that we're about 30 minutes over the official end of the session, but so maybe we could end soonish and the recording and then the sessions privately.
Yeah. Let's end the recording. And to be honest, I'm also kind of getting tired, so I think I won't be taking more questions at this stage. But of course, everyone are welcome to like talk to me offline, and we can like discuss that.